We're in the last week of Bootcamp. This is week 4. Did you guys know that? We started this on the 27th of June, and here we are. All right, let's do the homework. So a few of these should be pretty easy from the other week. So using the ERA data frame, let's just make sure I have that in there. Use correlation, central tendency, and other academic sets to describe how K per 9. That's my K9 variable here. So do that in a handful of ways. So K9, we can use correlation, central tendency, and or academic stats like t-tests to describe how K9 correlates with ERA. So I'll just start out with the central tendency stuff. So ERA K9, that's dot describe. That helps us do some of our summary statistics here. That gets me mean, that gets me median, that's the 50th percentile. Our interquartile range, and then our min and maxes, right? We can do some correlation stuff. So if we just import from scipy.stats, import, we can do Pearson R, we can do Spearman R. Either of those will work fine here. You can do Pearson R, ERA, and then we'll go the correlation of ERA and ERA K9, strikeouts per 9. And give me my Pearson R. All right. And remember to get that R value, you can always index to it. And if you want to get R squared, you just square it, right? And then if you want to get that stat, the statistic, it's that last value in there. And you kind of put it all together here. So that's one way. You could do this with Pearson R as well, or sorry, Spearman R. You get the same stuff. And then, of course, a couple other ways you may have tried. If you just did some sort of scatter plot or a reg plot here. So you could also do some sort of reg plot here. So many ways to get to the correlation. And then another way is if we had ERA and K per 9 in there, and then we did the core, right? So just another way you could get to that correlation. That's the same here as the Pearson R, right? 0129, 0129. Wilcoxon sign rank test is a non-parametric stat similar to Pearson R. Import it and use it to find the Wilcoxon value when comparing ERA and FIP. Okay. Easy enough, y'all, easy enough. We're gonna go from SciPy stats, import Wilcoxon. There it is. And then just like ERA, or just like the Pearson R function and the Spearman R function, no difference, still the SciPy stats package. So if we do ERA and we do FIP, there's our Wilcoxon sign rank test. And then the graph we made with the function makeCore, it doesn't have any way to identify which graph belongs to what data set. Right, so here's makeCore. Let's copy this down here. Identify, add a parameter in the function to add insert a string into the title. Okay. This is a little tricky for those who were uncomfortable with the function stuff. But let's take a crack at this and show y'all what it looks like. I had trouble with this one, okay. This is one of those ones where it's like, it's easier than you think, okay? So here, makeCore. So all this is asking for, right? When it's asking for add a parameter in the function to insert a string into the title. Remember that the title here, this title function, has this title string, and we have this entire thing here. And there's the, like, we did the f strings, right? And then you could insert variables like r. We're using experiment r here, t, we insert RMSE. So these are all things you can insert. If we have a function and we want to insert, say, a title name, say we wanted to insert just an arbitrary title name, like title name. You can actually just set that as a variable, title name equals whatever you want it to be. And so now, if we type here title name, and we say like ERA, you'll see that the title name now is inserting our title name keyword parameter, or key parameter here, into our title string. So this is just part of writing functions. Writing functions was the new thing the other night. So being able to take the title name, a variable inside of it, and then just like using f strings, we were able to insert a bunch of different things, mostly variables, values, but title name is also a variable, but this time it's a string variable. So so long as we have it in our function, we could kind of name it whatever we want. We could name this Andrew Spears, and we could name this one King Trey 90, and we could name this one ICU Hanley 13. And so now we could put in what the data set is for each of these different sets, right? All right, let's go into day 6, y'all. It's awesome to see so many people in here finishing up the last week of Bootcamp. Let's go dive into a little more statistics with linear regression, and then we'll touch base on what you can do with linear regression in terms of predicting outputs, right? First thing we want to do, as always, we're going to use that ERA data frame. So here's our ERA data frame. It should look something like this. So you should have like ERA in there. You should have FIP in there. You might have strikeouts per 9 in there. So those are all good things to have. So let's go over some of the things we did the other day. So if we want to just bring in from scipy.stats, and if you've done this already, great. We'll bring in Pearson R, and then if you haven't brought in, import Seaborn as SNS, import matplotlib pyplot as PLT. If you haven't done these things, go ahead and do that now. Let's just create some correlations. So if we want R squared, we could do Pearson R, ERA, and then if we want to do, let's create a new variable called call, short for column, and let's use FIP. So that way we have a parameter here, right? We have a variable here. Oh shit, this is square brackets. It is not square brackets. This is like this. And then remember, that first index in Pearson R is the R value, and then we're gonna square it. So this is R squared. Just like that, you should be seeing some value like 0.325 for your R squared. And then if we wanted to make a scatter plot, all right, data equals ERA, X equals ERA, and then Y equals call. Okay, and then do PLT show. So now we have this scatter plot, looks something like this. Okay, and then if we want to put in a title, and then we're using our F strings, I just want to say what the R squared is. And so I could just type in R squared, And then maybe we want to round that off. And we'll round it off to the 3 decimals. So now I have a plot that looks like this with r squared as the title and the scatter. So notice how I've parameterized this. So say I wanted to do multiple plots. We did this before, remember, with Hunter Green and doing the pitch plots. If you remember, we picked a bunch of different pitcher names and then we plotted the same bar graph multiple times. Shout out to that day. You thought I wasn't gonna go back in time. Here we are. Skill check pop quiz for column, for call. And we're gonna make a list and say we do FIP. All right, I'll do K per 9 since that's in our data set. Let's see, here, FIP, K9, and then we could just do walks, just walks in general. Okay. So if we did all 3 of these, and then we ran through this in a for loop, remember for loops, y'all. We have FIP, this correlation here. Here's K per 9. All right, this is part of the homework. And then here's walks, right? Which looks kind of like a weird Dorito shape. So we want to estimate what ERA is. And two things that we kind of have going for us, right, is our FIP value, right? There seems to be some correlation. We also have like this strikeouts per 9 value, which has no correlation, which is, it's weird because, like, you know, strikeouts, it seems like to be an important piece of earned runs. Like if you have more strikeouts, maybe you have less earned runs, right? So I want to use these two things to predict or to estimate what the ERA is. And if you just do these like correlations, right, you could kind of say like, okay, well, this has a correlation of this is a correlation of maybe, you know, if you squint, it could be like this has a correlation of something. But what we really want to do is we want to incorporate all of that information to one equation, right? And I'm gonna write this equation down, and if it's been a while since you've done algebra, then this will be a throwback for you. But we're gonna use this equation here called the slope-intercept formula, also known as y equals mx plus b, okay? So we're gonna use y equals mx plus b today. When we look at something like a scatter plot, we know y is on the y-axis, right? And then x here is a value on the x-axis. The m is the slope, right? Someone out there, like, okay. Slope is like the rise over the run, or the rate as to which a value is increasing or decreasing, right? This is a multiplier of some sort onto the x value. And then b, which is typically thought of as like an error term of some sort, or not error, this is typically thought of as the y-intercept. So where on the axis does where x equals 0, where does y cross? All right, if x equals 0, what is y, right? So that's the b value. Y equals mx plus b is sort of the crux of linear regression. Linear regression is just every time you add an x term or a feature, you're adding more x's, right? So if I wanted to add not just FIP, but if I wanted to also add another variable, I would just add another x term, okay? So for example, if ERA, right? If ERA, if we're doing y equals mx plus b, right? And then this is in, let's write this in plain English, right? ERA, mx would be like the weight of FIP, and we'll get to how to find the weight in a second, times FIP plus some sort of the y value where x equals 0, right? So that's ultimately what ERA would be, is the weight of FIP times FIP plus where y value equals 0, right? And you can see here, what would that be? Well, if we did it, we could actually apply this just like how in day 5, all right, we were applying different terms to create FIP in general, right? So we were able to like divide through things, add things together, multiply through variables. So we could do the same thing in our pandas data frames, right? So if I just say some sort of weight times FIP, that's great, but how do we find the weight? That's the biggest thing, right? How do we find this weight? Let's work on how to find this weight. And the easiest way to do that is to use some sort of package that does it for you. Let's import our first machine learning package, or rather it's a linear modeling package. So we'll do from scikit-learn, sklearn.linear-model, import linear regression. If we want to use linear regression, we kind of have to set up our, we're going to call this a model. So we're going to have to set up our model in a way to take in this linear regression thing, okay? So we got to do a few things first. And so bear with me, but we're going to use a lot of the things that we've learned before, okay? So we're going to reach back into the previous 5 days. So the first thing we want to do is, you know how we have the variable, right? You remember how to do variable things, like x equals 1. We're going to use a variable a lot called target. So this is my target variable, the thing I want to predict on, right? And so my target in this case is going to be ERA, because I want to ultimately predict ERA, okay? Now, I'm going to have another thing called features, and we're going to use a list, similar to how, you know, how we just used a list here to loop through all of our different correlations, right? I'm going to use a list here as well, and I'm going to put in the things I want to put into my linear regression. In this case, I'm just going to use FIP for now. But if we wanted to add like walks in there and stuff and K per 9, you could do that later, and we'll do that later in the session. But to keep it simple right now, let's just do FIP just for the purpose of the education here, right? So our target, it's just a string, because we're going to be calling a single column or a series of data from our pandas data frame. And our features, it's in a list, because we could have one feature or we could have many features. And so a list allows us to put more features into our model. In this case, like the target, right, is ERA. That's our y variable in y equals mx plus b. Features is our x variable, or x term in this case, right? And then the model, linear regression, is going to solve our m term and our b term, our coefficient and our intercept. Okay, so we have a target and our feature, and you can actually always double check how it's going, just to see the head of your data set here. So notice I have features, it's a list, right? And if I want to add, if I want to also search for target, I couldn't just do features plus target. This is going to give me an error, because this is just a string. So what this wants is like one big list. So I could add two lists together. So I put it inside of square brackets here. So now I see era.loc. I'm selecting all my rows. We've done this all before. Now I'm searching through features, which is a list, and then I'm adding or concatenating another list to features. All right. So features plus target, and now I do .head, and I see I have FIP and I have ERA in there, right? That's my features and my targets. All right, so far we've set up all the variables for our linear regression. Let's now get into the actual modeling linear regression code, okay? So the first thing we want to do is we want to create a model. And that's going to be really easy. All you need to do is, just like how, you know, in pandas when we import something like pd.readcsv and we bring that in as df, Just like how we do target equals ERA, features equals FIP in a list. We're going to create a model, and I'm going to store that in a model variable. So we'll do model equals linear regression. And that's almost all of it. Now, in order to use our model, we want to take our x variables and we want to correlate and find how much the slope and how much the y-intercept is adding to, or how much it's creating an accurate prediction for our target. So using the information from our target, how close can we get? How much can we estimate based off our one feature? So that the way to do that is, in the world of machine learning, we call this fitting our model. So for a linear regression, we're going to fit our model, or we're going to use our x variable, and it's going to learn, right? This is machine learning. It's going to learn or estimate what the slope is and what the y-intercept is, okay? So that's easy as well. That's model.fit. This is a function inside of the model, model.fit. And we're going to use our features. We're going to fit our features. So use that .loc notation. And then we're going to locate, or we're going to estimate our target. So again, model.fit, we're going to fit our linear regression with our x variable. We're going to use .loc notation. This first thing in here is x. So all of our x variables. In this case, we only have one. It's just FIP. Comma, ERA, and then the target. So this shouldn't be that complex because we've done functions already. You can write, because it's just, yeah, so, and I can show this to you as well. So for example, if we're just doing area.features, this is a data frame, right? And that's what model.fit wants. It wants a data frame. And then the target is going to be a series. So it just wants a single row of columns, right? You can think about that as like the y value. It just wants one y value, and it's going to take into account as many x values as you want to give it, right? So in this case, our series, ERA target in this case is the ERA, is just one value, one continuous string of ERAs, one continuous series of ERAs. And then our features, again, this could be multiple features. So we're only using FIP in this case, but we'll go back and we'll use strikeout as well. So we're putting all of our data frame in here of features, or x terms, and we're locating onto this y term. Now we could run this, and you should, if you're in Colab, you might get something that looks like this. If you don't see anything, that's fine too, so long as it ran. Personally, I'm not the biggest fan of this output, but some newer versions of scikit-learn are doing this. So if you see this, that's fine. If you don't see this and there's a green check, that's also fine. Once you fit it, you're actually basically done. Machine learning isn't that crazy. Before we plot, let's just take a look at our model, right? So we have this model, which is what it created. That's the session. So inside the model, right, there's a bunch of different things that the model has inside of it now. And one of those things is coef, which, as you can imagine, stands for coefficient. That's this m variable. Okay, that's slope, that's the coefficient, right? Some people call this a weight. And then there's another thing inside of the model, right? And it's the intercept. And notice how they give it to you, right? Coefficients, if there are multiple coefficients, then you might have multiple weights. And the intercept is that y-intercept, right? So where, when x is 0, where is y? And in this case, for FIP, y would be 0.85. And if we look at FIP and ERA, you know, if it's 0, yeah, 0.85, yeah, somewhere maybe here, I guess. Like if, you know, I don't know. We would have to like scale this to, it doesn't give me all, you know, here's 0, I guess. 0, 0. If I draw a line, maybe this gets me to like 0.8, a little below 1. Okay, that's believable. I can believe that. Okay, so we have this coefficient and we have this intercept. Now what do we do? Let's use this information. So we could take that coefficient, and I like putting it into a data frame called weights, or WS. So I'm gonna create a data frame with it. Okay. So we're gonna create a data frame called WS. Okay. This stands for weights. And I'm gonna put this into a list, or just square brackets, .coef. All right, model.coef. All right. But I want to set my columns to whatever my features were. You can kind of see here, this is a nice, neat, organized way of saying, okay, now I have a data frame of weights. My columns are the names of my features, and the weights are in this nice data frame. So if I ever need to call, hint, hint, if I never need to call my weights, I could always have it in this data frame, okay? And then likewise, I'm gonna store my model intercept as my B term, because it is the B term. It's y equals mx plus b. So this is gonna seem a little elaborate. If we were to do y equals mx plus b, right, and I have my data frame of coefficients, or data frame of weights, coefficients, I have my intercept, I could simply type, right, like whatever my feature is. So in this case, in features, right, I have FIP, right? To access it, I could get it out like this, right? So if I have a column called FIP, right, and I say, and we're gonna use our F string here, well, we'll do that in a second. If I take a column, right, of FIP, here's all my FIP values, right? But I want to multiply through all my FIP values with all the weight here. I would take this value, right? Here's the FIP weight, and I would just take the values. It's gonna give me this list. So sometimes I'll do this like values, and I index for the 0. So this is just a way to get it out of like the pandas series. I go values square bracket 0, and that gets me the number. Okay. So if I do this, or if you would rather do it this way, because it's m, this is the m variable, times x, and then we want to add b. So this is y, or sorry, this is m x plus b. This would give us y. And remember, we fit our model to what y should be. So now, if I do this, right, I'm gonna get a different value, right? This is a series that now is multiplied through by the weight, and I'm adding the b term. And you can kind of compare, right? If we just look like FIP here, notice how the first values here, they're a little different now. They're a little different, okay? So to put a cherry on top of this, I'm just going to call this something new. I'm going to call this my prediction, but to be even more explicit, I'll use an F string, and I'll say my target prediction, right? So if I'm reusing this code at all, if I change what the target is, it's going to make me a new column. So this is all like reusable code, and we'll get to that in a second. So now let's run this code. And then now we have the actual, and we also have our predictions or expected. What if we take a look at a new scatter plot, right? First, let's take a look at ERA.head, right? So here's ERA, here's FIP, and here's our new ERA pred column. So you should all have this new ERA pred column now. And so if I use my scatter plot, data equals ERA, X equals the target, because the target in this case is new. It's our ERA column. And if we use that F string again, and we say target underscore pred, okay, and we show, now we have ERA and ERA pred, and this looks a lot like our FIP graph. So if we do target and then we looked at FIP, right? Notice how similar it is in terms of just where they are in space. Now the values might be, the values are the same, but that's because FIP and ERA prediction, right? That's only one thing we're using. And so it makes total sense that FIP and ERA pred are just the same with a little difference in the weights. This is maintaining that correlation. Let's do it again. And this time we're gonna use more features, okay? So we're gonna do it all again. We're gonna combine cells now. I'm gonna do this all again, but instead of just using FIP, let's do FIP and strikeouts per 9. Okay. So we'll use ERA, and then we'll do FIP with strikeouts per 9, okay? So now we have 2 features in there. I'm just gonna copy a bunch of stuff that we used before, okay? We have our model fit, right? We have a way to get our weights. And remember, this is all reproducible code, right? This is all stuff we could take from above. And we'll do this after. Okay. So we're gonna use FIP and K per 9 now as our features. And then when we run through this, it's gonna fit our model with our 2 features now, not just 1. And then we're gonna get the coefficients, right? Now, I do wanna go over something about y equals mx plus b. And some of you may remember this, you know, if you got to like a certain point in linear regression, sometimes y equals mx plus b isn't always just y equals mx plus b. If you wanted to add multiple terms, right? Sometimes you'll see, you'd see the notation like y equals m1 x1 plus a second term with weights, right? Dot, dot, dot. All the way out to however many terms you want plus b, right? So you could have multiple things adding together to predict your y value. So in this case, we have 2. If we look at our weights, we have FIP, and now our weight is a little different. And we have K per 9, and we also have a weight here. So this would be like the weight for FIP plus the weight for K per 9. So this equation here becomes harder to replicate, right? Because this was only set up for one iteration. So if we do this in multiple steps, we could probably do this a little more accurately. Okay, so we're gonna steal a little from our code, except in this case, we're gonna create a for loop. Right, so I know features has my 2 features, so I'm gonna loop over my features. Okay. And then I'm gonna multiply through by the weight, but I don't wanna add B, because I wanna add B at the very end. You only wanna add B one time. So I'll multiply this through, and then we're gonna just create a column in my data frame called weight, or W, or sorry, we'll use the same notation. Column with the F string W. Okay, so when we take a look at the head now, at the end of this, we'll have FIP W, K9W, right? And this is the weight times the column, right? So this is M1, X1, M2, X2. Now, at the very end of this, if we want to add it together, we would take array FIPW plus array K9W plus B, right? So this is now this term plus our B term. And this is our new target pred. So we're just gonna overwrite our old one, okay? So now we have a new array pred, and then if we take a look at our new array pred, look how much more correlated it is. All right, look at our prediction, array versus array pred. Before, it was just looking like FIP, and now it's looking stronger, right? So what if we were like, oh, that's fancy. Let's get some statistics on this. Pearson R, right? array target, array target pred. And in that first index, we can get that square. Let's get that title in there, F strings, R squared. We'll round the R squared by 3. And now when we plot this, we're getting that 0.404. 404'd. If we want to go even one step further, we could use our friend mean squared error. Right? Same stuff, and then raise to the 0.5 so we could do the root. Okay. Title string. Separate this down. My RMSE now, round R2, oh sorry, our MSE 3. This is an F string. We did this all in the plot the other night. Now I have title string. Look at that. Your RMSE in there, and then you also have your R squared in there. All right. All right, if we're all good here, if we're all good, and we got 30 minutes, let's jump ahead. let's grab some of these columns we were working with before. So we're working with our target and our features, and then we're working with our linear regression and our fit. Okay. And from here, what we did before was, where the heck was I? What we did was we grabbed the model coefficients, we grabbed those weights, we got the intercept, and then we by hand calculated the prediction for this information. However, you don't have to do this every time, because if you say had hundreds of variables, this would be a little more hard to construct and be hard to, well, not too hard, but it would be more cumbersome to maintain if only there is a way to take all the information from the model and predict the variable. Well, luckily for us, there is. It's called predict. So for example, if we wanted to take all our features and then we wanted to predict over them, so we train our model, it grabs all of the weights, and then I wanted to see how close our prediction is. If I run model fit predict, we get a column of data here. And I can set this equal to ERA, our target pred. Okay. And if I take a look now at our graph, right, the same graph we did before, you might be wondering, like, well, these are identical. Well, you're right, they are identical because it's the same math, right? So we're taking the coefficients, multiplying through, and adding our error term. Under the hood, fit and predict, they're doing the exact same thing, right? Predict, model.predict, is doing the exact same thing as us multiplying through by the weight, adding all of the weighted columns plus B, creating our prediction column, right? It's doing the exact same thing. It's just all in one equation now, all in one function, okay? So rather than doing all of this by hand, right, we can actually just do all of this in one function called model.predict. So really, machine learning in this case is wrapped up in these 5 lines, right? Single or double doesn't matter, it's just styling, interchangeable. So these 5 lines are ultimately like the crux of machine learning. You have a target, you have your feature set, you have your model that your machine is learning, training your model here, and then you're predicting based off your model training. Okay, so this is like really the totality of machine learning here in as simple of a form as it can be. Select your features, select your target, fit, predict, and then let it rip. There's more lines to plot the validation of your original data frame and your other data frame, your prediction data frame, or your predictions, your actual values and your prediction values. There's more lines of code here than before. All right, let's go to the next part. Okay, remember our train and test data frames? Shit, I should have copied that when I was back here. Or our train and test data frames. So we'll just take a random sample of 100, and we're using random state 1 for a train data set. I'll take a random sample of 100 from a random state of 2 to get our test data set. Okay, we'll treat these as 2 independent samples, so to speak. Let's pretend that this comes from one season, this comes from a different season, you know? That's the situation you might be in. So let's apply what we just learned. Okay? So we have our trained data set and our test data set. We could fit to our training data set. So we train the model on our training data set. And then on our test data set, this is all of the information that the model hasn't seen, right? So you can think about this in many different ways. You could think about this like, say we only have data up to today and we're trying to predict what happens tomorrow, all right? You'd use all the data up to today, and then the prediction here would say, okay, well, given all our information, what would happen with our best guesses for what's gonna happen tomorrow? And this might give you the information for tomorrow, right? So in this case, if train was 100 pitchers from last year and test is 100 pitchers from this year, like how well can we estimate from our train data set to our test data set, from one set of information that is separate from another set of information, okay? So let's run through that. Okay. Again, it's just these 5 lines. All we did was change the model.fit into train instead of ERA. And then we changed our predict code to our test. Okay. And now we'll do the same thing here. We'll go to test. So we'll change all the places where this says ERA to test. And here's our estimate, right? So this is pretty close to what we would think. We know that the correlation in total, these things predicting onto ERA has an R squared of 40% explained variance. We're getting near that with just 100 pitchers from one set of data and then 100 pitchers from another random sample of data. So this is showing me, like, given the information we have from one data set, we can predict over something that's happening in another data set. Does that make sense? Are you feeling okay? So rather than using just one data set and describing what's happening in one data set, we're using 2 different data frames. One of them we are using to fit our model, and the other data frame, which this model doesn't know about, it didn't train on it at all, it wasn't fit on this data at all, we're saying, all right, take my information from test.loc and give me what you think their ERA is going to be based off their FIP and their strikeouts, right? And just to prove it to you, right, here's our head for our train data set, and here's our head for our test data set, right? We should get a fairly good random sample between these 2 data sets. I would expect only like, 10 or so of these pitchers to overlap. All right, homework time. This is the last homework of the bootcamp, chat. Let's use different train and test data sets. Using random state equals 10 and for the train data set, and random state equals 20 for the test data set. Predict ERA in the test data set using strikeouts per 9, walks, and home runs. Home runs and FIP using linear regression. Visualize your prediction by showing actual ERA on the x-axis and your predicted ERA on the y-axis. Display R squared and RMSE in your graph. Okay? That's the only homework, because this is all pretty hardcore already. Today was easily the hardest day, right? Even though it was maybe the least amount of code, I think today was the hardest day. The hardest day so far, yes. Who knows what will happen on Thursday? It's not resume prep.